Hello students, in this video we'll consider the question of geodesics on surfaces of revolution. Let's consider the geodesic equations. The geodesic equations are d squared xi dt plus gamma I j k dxj dt, and then dxk dt is equal to 0. So these are the geodesic equations, right? And so let's look at some simple example of surfaces to see if we can figure out what the geodesics are. So of course, what are the prototypical examples? Well, of course, you think of the trivial example just like a plane, right? So the simplest example is just a plane. Then gamma I, j, k are equal to 0, and you get straight line solutions. So straight lines, because you have the second derivative is equal to 0, right? Excellent. Let's do the next simplest example, which of course is just where you take a plane and you roll it up into a cylinder, right? If the surface is a cylinder, then how can we parameterize the cylinder? Well, it's easy to parameterize, right? I'm going to do a classic surface parameterization just of u and v, and that's going to be what? It's just going to be a cosine of u, cosine of sine of u, of course. I need a cosine and a sine. Sine of u, and then v for the radius. Okay, so this is going to parameterize our unit cylinder, like so. There are rulings. Of course, this is a classic surface of revolution. You're just rotating a line, right? Of course, it's also a ruled surface, right? So there's our unit cylinder over here. It goes on forever, okay? I want to know what the geodesics on this thing are. So let's look at sigma u to find the first fundamental form. So of course, sigma u is just going to be negative sine u cosine u 0. My sigma v is going to be just a 0, 0, 1, right? So we see that these partial derivatives are perpendicular to each other. So I have a standard metric, right? So my metric over here, ds squared, is going to be sigma u dot sigma u du squared, plus, then of course the cross terms are 0 because when you dot them you get 0, plus sigma v dot sigma v dv squared. Of course, sigma u dot sigma u is 1, sigma v dot sigma v is 1, so this is just du squared plus dv squared, right? So my gij is just delta ij. So my gij in this instance is delta ij, okay? And so that forces all the Christoffel symbols to be what? Gamma ijk are all equal to 0 on a cylinder. All the Christoffel symbols are 0 on the cylinder, right? So Christoffel symbols vanish on a cylinder. Okay, excellent. And so now, of course, what can we do? Now, what are the geodesic equations? Well, now the geodesic equations are very, very simple, right? They're going to turn into what? They're going to turn into u dot dot is equal to 0, and v dot dot is equal to 0. So u is linear, c1 plus c2t, and v is linear, c3 plus c4t. I completely solved the geodesic equations on the cylinder, right? So of course, what does that curve look like over there? Well, my u is linear and so is v. So my curve over there is what? My curve gamma of t, my geodesic curve, or sorry, geo for this curve, is going to be what? Is going to be the cosine of u, which is c1 plus c2t, and then the sine of c1 plus c2t, and then c3 plus c4t, c3 plus c4t. And of course, what is this curve over here? This curve is just a circular helix. Okay? If, of course, what? So, of course, if C4 is non-zero, right? So if C4 is non-zero, and these coefficients are not 0, because, of course, we can get sort of simple cases, too, right? We can get these, like, straight vertical lines up and down. We can get these parallels over here, right, with those circles. But in general, we see that if I want to go from here to over here, where they're not on the same circle, they're not on the same line, to do that, we have to follow a helical path to get from there to there. And that helical path is our geodesic. Beautiful. Okay, so the geodesics on these cylinders are what? Are either helices, they're circles, or they're the rulings. Okay, so that completely classifies what the geodesics are on a cylinder. But now I want to illustrate to you that for a general surface of revolution, the situation isn't as simple. In other words, I can give a complete characterization, but in terms of sort of implicitly defining what the solutions of a second order system are, right? So in general, suppose you're given a curve. You have what? You have, well, the curve will look like, let's say it's f of u, and then 0, and then g of u. That's my curve in the xz space, where f dot squared plus g dot squared is equal to 1. So it's a unit speed curve. And then we can parameterize the surface, right? The surface is going to be sigma of u and v is going to be f of u cosine of u, then f of, that's a v actually, I'll put a v there, not a u. F of u sine of v, and then g of u like that. And then, let's see, we have this messed up a little bit, so let's change the parameterization. Let's change that parameterization, right? So what will this be for the surface of revolution? So, good, so we're going to rotate in those coordinates over there. So we'll have f of u cosine v, f of u sine v. There we go, much better. And then g of u. Like that, okay? Because the z component stays fixed. So what's sigma u going to be? So sigma u is going to be f prime. I'm going to suppress the notation. Well, it's not. Cosine v, and then f prime of u sine v, and then g prime of u, like that. What's my sigma v going to be? My sigma v over here is going to be an f of u sine v negative, an f of u cosine v positive, and then a 0. Now clearly these vectors are perpendicular to each other. You can check this because I have a negative fu f prime u cosine v sine v, and then I have a positive fu f prime u sine v cosine v, and then 0 over there, so they're perpendicular to each other. And what will the uu component be? The uu component is going to be what? It's going to be f prime squared plus g prime squared, so that component is going to be 1. So my ds squared for this is going to be what? So if I dot this with itself, I'm going to get f prime squared plus g prime squared. Since it's unit speed, that's going to be a 1, so I'm going to get a du squared. Good. And then what will the vv be? It's going to be quantity f squared. Yeah, so it's going to be f of u quantity squared. So plus f of u quantity squared. dv, like that, okay? So that's my metric. So now, of course, to find the geodesic equations, I need to look at the Christoffel symbols, right? So, of course, what's my GUU is going to be 1, and my GVV is equal to f squared of u, right? So let's look at all the Christoffel symbols over here. So I have gamma, u. What's that going to be? So that's going to be the u derivative of what? Of the log of the u component with respect to u, and that's just going to be 0 over there, right? If I did this, if I did gamma u, v, then I'm going to have the v derivative of the u component. That's also going to be equal to 0, okay? If I have gamma of u, v, what will that be over there? Well, that's going to be negative 1 over 2, and then the what? And then I'm going to have a u component, which is going to be a 1, and then I'm going to have a derivative of the vv component over here with respect to u. So that's going to be a 2 f of u f prime of u, like that. So this u f vv is going to be what? The 2's are going to cancel out. It's going to be negative f u f prime u, like that. Okay, great. Those are those Christoffel symbols. Let's do the other Christoffel symbols over here. What will gamma of v be? That's going to be the v derivative of the log of the square of the v component, so that's going to be 0. What's my gamma of v, let's do a u going to be? It's going to be a negative 1 over 2. And now I put an f squared over here, f squared, because it's going to be the VV component, so f squared of u. And then I'm going to have the derivative with respect to v of the first u component. So that's going to be times the 0, so that's going to be 0 as well. Okay, good. And finally, what is the gamma v u? That's going to be the u derivative. It's going to be the u derivative of the what? Of the log of the square root of this thing over here. So it's going to be the log of what? Of just f of u. So that term over there is going to be what? That's going to be f prime of u. That's going to be f prime of u over f of u. Okay, great. And so now what are the geodesic equations going to be? So let's take a look carefully and see what they're going to give us. So we're going to have the u dot over here. So we have u dot dot. And then the only u term that survives is the VV term over here, right? So then I'm going to have a minus f of u, f prime of u, and then v dot squared over here. V dot squared is equal to 0. And then what we have over here, then we have a v dot dot, and then a plus what? Now I have two of these things over here, so I have 2 f prime of u over f of u, and then that's going to be a u dot and a v dot. U dot, v dot is equal to 0. So those are the geodesic equations for the surface of revolution. Now, unlike the case of the cylinder, I have these components over here to consider. One really important case to understand is the case when you have v dot being equal to 0. So if v dot is equal to 0, both of these terms over here, if either v dot or u dot are equal to 0, then both these terms over here are going to, this term over here, so if I, in particular, if I have v dot equal to 0 along a meridian, so if we're along a meridian where v dot is equal to 0, then this term is gone, this term is gone, this term is gone. So in other words, the meridians are automatically geodesics. That's the only thing you know, right? The question becomes, when are the parallels geodesics? Well, you're going to need one of these f of u or f prime of u's to vanish in order for these systems to work. So with these geodesic equations over here, we can see that depending on what the function f is, the function g plays no role. It's just the relative distance in the xy plane over there where the rulings occur. So solving these equations in general will provide you the solution to the geodesic equations, and we're going to see in further videos this Clairaut theorem, which basically characterizes these geodesics in terms of tangents at points where the meridians intersect. Thank you very much.